Let's jump right in. Welcome to today's Explainer. We're looking at some incredibly cool, honestly, groundbreaking research from a recent study on machine learning for biometrics. We're going to explore a really fascinating challenge, how artificial intelligence actually learns to recognize growing children over time. Think about it. Even human relatives struggle to recognize a kid if they haven't seen them in a few months, right? So this isn't just a technical puzzle. It's a profound intersection of computer science and, well, real human welfare. All right, let's get into it.
So, how exactly does an AI recognize a missing child when their face is literally changing every single month? This is what scientists call the longitudinal face recognition problem. See, when an adult goes missing, their facial structure stays pretty static. But toddlers, their features evolve rapidly. Their proportions shift dramatically in just a matter of months. And this presents a deeply emotional, but also incredibly complex problem for researchers trying to build machine learning systems that can track these kids across different periods of time.
Here's our quick roadmap for today. We'll start with the Missing Child Challenge, look at traditional methods like PCA and LDA, then dive into the deep learning upgrade. After that, we'll see how to optimize the CNN model, and finally, wrap up with the real-world impact and safety.
Number 1, the Missing Child Challenge. Basically, tracking faces that never stop changing.
Robust facial recognition for children serves some absolutely crucial roles. We're talking everything from tracking healthcare services for infants to, obviously, aiding in real-world investigations of missing children. But the core bottleneck here is biology. According to the source material, a child's facial development actually begins as early as 3 months in the womb. But as they grow, this development isn't proportional to the rest of their body. Because their faces change so unevenly, recognizing kids under the age of 6 remains this incredibly difficult open research problem.
All right, moving to Section 2, Traditional Methods, PCA and LDA. We can think of these as the old-school detectives.
So early researchers had to rely on 2 foundational techniques. First up is PCA, or Principal Component Analysis. It's an unsupervised algorithm. It doesn't use class labels. Instead, it just tries to reduce the massive dimensions of an image to find the most critical linear variables. Then there's LDA, Linear Discriminant Analysis. This one's a supervised enhancement of PCA. It actually uses those class labels to better separate different identities. Basically, these old-school detectives are trying to match a face to basic sketch outlines using linear math.
I know the concept sounds a little bit ghostly, but researchers calculate what they actually call the average face. To get this, they take a standard face image, 224 by 224 pixels, which flattens out into this massive vector of over 50,000 individual data points. The PCA algorithm then calculates the average of every single face in the database to create a baseline. Every new face is then compared against this slightly creepy average baseline to see exactly how it differs.
Once that average is calculated, the traditional machine learning model breaks faces down into a grid of what we call eigenfaces. These represent linear facial variables. Essentially, the computer is using these calculated masks to figure out the unique linear traits of a child's face. The problem, though, this process is incredibly computationally heavy, and more importantly, because it relies heavily on linear variables, it really struggles to keep up with a growing toddler whose facial geometry is constantly and non-linearly changing.
Which brings us to Section 3, the Deep Learning Upgrade. Basically, our modern forensic team.
The contrast here is just night and day. Traditional machine learning, like PCA and LDA, is completely limited by linear dimensionality reduction. Plus, it requires tedious manual face cropping just to even function. Deep learning, on the other hand, specifically convolutional neural networks, or CNNs, automates this whole process. It bypasses the manual labor to learn complex, nonlinear features entirely on its own. While traditional methods kind of buckle under the computational complexity of tracking every changing pixel, a CNN automatically and efficiently hones in on the distinctive features that actually matter.
So, how exactly does it pull this off? Through convolutional layers. You can think of these layers like a modern, highly trained forensic team. The very first layers of the CNN learn to recognize incredibly low-level features. We're talking just simple lines and edges. But as the network gets deeper, layer by layer, it combines those simple edges to extract high-level, complex facial geometry. And it does this completely autonomously, which makes it an absolute game-changer for tracking the constantly evolving features of a growing child.
Section 4, Optimizing the CNN model, or breaking down the black box.
To actually make this work in the wild, researchers use 3 key optimization steps. First, we have those convolutional layers extracting the features. Second, they add batch normalization. Because look, in a missing child case, investigators do not have weeks to wait for a model to train, right? They need rapid, efficient identification. Batch normalization drastically speeds up that training process. Third, they use L2 kernel regularization. This is absolutely crucial because it prevents the model from overfitting. It stops the AI from just memorizing the training photos, so it can actually recognize the child in a brand new, never-before-seen photo.
The data shows exactly why this optimization is so important. If we compare the kind of erratic performance of a basic CNN to a highly customized version, the difference is totally obvious. By using data augmentation, cropping and flipping images to give the AI more diverse examples, and by expanding the network to 6 convolutional layers, the model's learning process stabilizes beautifully. The accuracy metric stays high, and the loss metric drops and stays low.
Which leads us to the staggering number, 94%. By optimizing the CNN with those extra layers and regularization techniques, the cross-session facial recognition accuracy, which just means the ability to recognize a child from a photo taken months later, jumped from a pretty basic 86% all the way up to an incredible 94%. That is a massive leap forward in ensuring the tech actually holds up when serious time passes between photos.
And finally, Section 5, Real-World Impact and Safety. Tech to the rescue.
Ultimately, the automatic recognition of children using their faces is a tremendously useful investigative tool to help identify missing kids. All of these complex, computationally heavy deep learning systems really have one singular goal: directly empowering law enforcement agencies and healthcare providers. They're basically turning a static database into a dynamic, life-saving tool that can actually cut through the biological reality of a child's changing face.
So I want to leave you with this final thought. As our data grows and our algorithms become even deeper and more optimized, how many more lost faces will finally be found? The potential here to save lives and reunite families is just awe-inspiring. I really hope you found this breakdown as fascinating as I did. Keep questioning, keep learning, and thank you so much for joining me on this explainer.